So our first speaker, his name is Joan Serra. He's a research scientist at Telefónica. He works within time series, audio, tagging, and social data, so quite a bit. Has a Ph.D. from UPF, has co-authored more than 100 papers, and one of his papers that he's going to present here today was accepted to this year's ICML. So please give a warm applause to Joan Serra.
I'm pleased to present you this work that was presented last July in ICML in Stockholm, and of course available on archive several months ago. Let's just start with the introduction. So this work deals with the problem of catastrophic forgetting, and you may not be familiar with it, but it's actually a quite old problem. Since the end of the 80s, beginning of the 90s, people realized that machine learning algorithms, not only neural networks or deep learning algorithms, but machine learning algorithms in general, were forgetting what they were learning. Meaning, I give you an example. So, for instance, let's assume this trivial case. So here you have assume images of cats and dogs, and you only have two features, okay, and you can learn a classifier. In this case, let it be a linear classifier to separate between the two classes. And then you move to a new data set, you get a new data set, and this data set contains cars and houses. And you take the classifier you had learned before, and now you train it on this new data set. It, of course, perfectly distinguishes between the two classes. But now, what happens when you put into the classifier the images you had for the previous data set, that the distinction doesn't work anymore. It has forgotten the previous distinction of the data. Of course, this has strong implications for more general artificial intelligence. So I personally believe it's quite unrealistic to expect that we will be able to train any decent autonomous agent with all possible data of the world in parallel, training that in parallel. So the only way with so many things to learn in this world is to learn sequentially, like humans do. And to learn sequentially, you need to remember what you learned in the past. You shouldn't forget. So since this problem is a little bit old, so there has been a lot of people working with that. Here I'm going to just briefly summarize some more or less recent works. But they are based also on some principles that were already, some of them were already applied in the 90s and so on. So one way to combat this problem of catastrophic forgetting is to use what is called rehearsal strategies. This basically involves the use of some kind of memory. And then when you learn the new data set, you exploit past memories in order to keep remembering the past while you learn the new data set. And there are also some strategies which are based on what is called pseudo-rehearsal, or dreaming, if you want. So with these strategies, you learn to generate data like the one you saw in the past. And then while learning a new task, you can always generate past data and then keep on training concurrently on this data. But this doesn't prevent you of this parallel training. So in order to learn the new task, you need to include all the past data. It's not truly sequential. Finally, there are a group of approaches which I term them that they try to reduce representation overlap. And inside this type of approaches, there are two types of approaches. One is more related to structural regularization, regularize your models so that you don't forget. And another type of approaches work more directly on neural networks. And what they do is that they try to freeze some parts of the neural network so that these ones don't get altered when you learn a new task. And then other parts are freed so that they can learn a new task. And the approach we proposed is within this type of approaches. But before explaining our approach, I will give a 2-minute summary of 3 works before that are quite similar but substantially different to the one we propose. The first work is this one by Google or DeepMind, I don't remember, progressive neural networks. So this concept is very simple. So this works in columns. So for the first task, this would be the purple network here. You learn a network in a kind of column. Okay, for the second task, you freeze the first column. You learn a new column plus some adapters that are going to be able to reuse the information from the previous network. And for every new task, you keep applying this technique. And of course, this has the problem that it grows in the number of parameters. This is totally unrealistic, okay? But it works very good. I mean, it's a very strong baseline because you never forget anything. You just freeze the whole network before. And thanks to these adapters, the new network is able to efficiently combine previous knowledge with current knowledge. There is another work, also by the same group, which is called PathNet. And in this case, what they do is that they compartment the neural network into blocks, and then they try to learn paths through these blocks, and these paths are data dependent or data set dependent. This way, you can train with one data set, you learn one path. This learning, by the way, is done through evolutionary strategies, but then the network is trained with stochastic gradient descent. So this approach is a bit complicated to train. And also, you need to decide on how big are the blocks, how many blocks you allocate for every possible building block of a neural network. And then if you have a very complicated building block, what do you do? If you have an RNN, it's not clear what would you do, et cetera, right? But it has also the advantages of progressive neural networks. So you never forget. You can freeze the blocks that you discovered were useful for some previous task in the past. And then you can reuse these blocks because nothing prevents that here I didn't draw it, but you can reuse blocks for new tasks. Finally, there is another approach, which is called PackNet. And this approach breaks the idea of using blocks. So basically, it works on a unit base. And what it does is that it first learns a network, then it tries to compress it, remove spurious connections. Then the connections that are not removed are kept and frozen. And then the ones that were removed are free to evolve and learn the new task sequentially. OK, so this is a basic summary of it. Now let's go with our method. So the main motivation was looking at this problem. We realized that, OK, let's assume this is our data set. And let's assume the first task is to distinguish between birds and dogs, like before I mentioned. Well, before it was cats and dogs, but anyway. So, OK, let's assume you learn this task well. And then suppose you keep the same data set, but you change the task. Now the task is to distinguish between brown and black animals. So clearly here, the data has not changed. But what's left, what has changed? It's the task. So why don't we introduce the task ID into the problem? So we shall exploit the task ID. Given that the same data set can yield to a myriad of tasks, we need an extra information in order to know in which task we are so that we can learn progressively. And this is the idea we do. So we learn embeddings per task, and we apply these embeddings multiplicatively to the units of the network. So in the first task, the embedding may tell us, look, these units, these neurons are super important for this task. Therefore, we keep them activated. Then for a second task, we know that these units were important for the past task. Therefore, we don't touch them. Now, in this new task, we learned that these other units are important for this new task. So we freeze them, we keep using them, and we are able to reuse previous tasks. This is a more detailed schema of the architecture. Here on the right, you have the regular network. So you have your layers. And we only add these multipliers here. And the structure on the left is what we develop. I will go a bit step by step. So first of all, we have an attention mechanism on the output of every layer. So this attention mechanism is just regular attention. The only thing is that it's a hard attention. So here, components, we want them to be binary. So we want the neurons to be either active and working for that task, or either inactive and not being learned for that task, so frozen. And the way we do it is just multiplying this embedding E by some constant S, and then applying a sigmoid signal and learning this through stochastic gradient descent. No change in the learning schema. So here, the objective of this embedding is to condition the output of every layer, and with the intention of making this output binary. We will see it's not really binary. Then, of course, when we learn the attention for the first task, and we learned the attention for the second task, we need to accumulate these attention vectors. This is the way we accumulate them. We accumulate them with this maximum relation here. So basically, this basically means if something was important in the past, never erase it, because if it reaches a maximum of 1, remember it's a sigmoid, you will never, that attention value will never become lower than 1, just because of this maximum operation. And importantly, the equation on below, we use the reverse of that, the minimum negated with the one before, to condition the gradients. Therefore, if we had an attention of 1 for a past task, in the next task, we will have gradient multiplied by 0. If we have an attention of 0.9 in the previous task, when learning the new task, in backpropagation step, we will have 0.1. So all the gradients will be divided by an order of magnitude. And then, yeah, so learning this attention mechanism, as we want it to be a hard attention, so ideally we want active or inactive neurons. This means that we have to deal with binary signals. Binary signals are not differentiable, so therefore the gradient doesn't flow. Therefore, we never learn this E vector here, which is the embedding. So how to do it and how to deal with this problem, and we propose a simple annealing scheme. So we have this gain S, and this gain S is epoch-based. So at the first batch, it's a normal sigmoid, S is 1, or some smaller value than 1, actually. And then once the epoch progresses, in the last batch, this S is very high. What happens when S is very high? Something multiplied by S, which is very high, is a very high quantity. When it goes through a sigmoid, it's a 1. So, and if it's something which is very small, negative, and when you multiply it by S, which is a very high quantity, and it goes to the sigmoid, the result is a 0. So in the end of the epoch, we are working in a kind of binary mode, but in the beginning of the epoch, we are working on a sigmoidal mode, and therefore the gradient can flow, and we can learn these embedding vectors. And of course, this introduces the gradient, but these gradients are rather poor. So they are not as if all the time it was a simple sigmoid without this binarization step. Therefore, to combat that, we design an analytical expression to weight these gradients to compensate for what would be the actual gradients. I will skip you the formulas here. They are in the paper. But basically, it boils down to apply the inverse of the sigmoid and then correcting for gains. And well, you will see it in the paper. And finally, and this is important, we don't want to dedicate too much capacity to a simple task. So we want to spend only the right amount of neurons for a given task. How do we do it? We introduce this regularization. It's an L1 regularization, which sparsifies our attention vectors. Not the weights of the network, not the outputs of the network, but only the attention vectors. This way, we make sure that attention is only put to few neurons, the fewest possible to solve the task. Plus, the network is allowed to use any weight value, which doesn't constrain in any way the weights of the network, and it doesn't constrain the outputs of the network, because this is multiplication. And in forward pass, ideally, it's multiplication by 0 or 1. So the rest of the network is free to learn whatever it wants. And yeah, this is just a fancy weighted L1 way to apply this. As I said, the objective here is to prevent dedicating all available units to a single task. So let's go to the results. So first of all, I want to say that in general, for evaluating catastrophic forgetting, we found that current approaches were a bit unrealistic, let's say. So they were using maybe always the same data set and performing permutations over this data set and considering this as a new task. Data sets sometimes were MNIST, which is not a realistic data set, etc. So I think we were the first ones to use really a long 8 different task data set and complicated tasks. So here you have CFAR, you have street view traffic signs, street view house numbers, etc. Then we also considered as many approaches as we could consider. Some competitors like elastic weight consolidation, which got very famous, the PathNet and progressive neural networks I explained before. And we tested two types of architectures, one convolutional, one multi-layer perceptron architecture, so to be sure that we were generalizing a bit beyond the multi-layer perceptron architectures that other people were testing. Also, since we were considering different tasks, every task had a different accuracy. So in order to measure accuracy across tasks and to study forgetting, we had to design a forgetting measure. And this is this measure here on the right. So basically, it's a measure that the best is 0, so you forget 0. And then if you forget 1, you have forgotten all. You have forgotten -1, sorry. If the measure is -1, you have forgotten everything, right? So we want something close to 0, but you can forget a lot. And yeah, I mean, we were performing 10 runs and computing statistical significance, etc. And plus, after our setup, we, of course, to present results, we also studied all the setups that are used in the literature, like incremental CFAR, this permutation of MNIST dataset, different splits of the MNIST dataset, etc. But that was just for complementing our results. So, and these are our results. So these are some basic baselines that forget very soon. So after the 4th task, you have forgotten more than half of the original accuracy. And these are the other baselines that they already perform very well, forgetting on average between 10% and 40% of the original accuracy. And the one on the top is our approach, which was outperforming them by quite a large margin. So here you have the forgetting ratios after 2 tasks, first column, and 8 tasks, second column, and the standard deviations. So apart from being much better than the competitors, our approach had quite low standard deviation compared to the rest. So this means that the approach was very stable with regard to different initializations, different partitions of the training set, the validation set, etc. So here, this implies that we were obtaining 75% and 45% reduction in forgetting with respect to the best baseline for this task. But then when we consider another task, you see that the best baseline of the previous task is not the best baseline now. So now the baseline is another one. But still, we are able to achieve a 50% reduction in forgetting against this other better baseline. If we switch the task again and consider the classical permuted MNIST task, so here, to compare with them, we cannot compute the forgetting measure, but we compute accuracy. And again, the method performs better when you match the number of parameters of the networks, otherwise would be unfair. And same for this split MNIST task. And then what else we do? We study the influence of the hyperparameters. So our method has 2 hyperparameters. One is Smax, which is the amount of binarization you introduce in your hard attention. It is how big you let S grow. The S is this multiplicative factor that we had on the embedding before the sigmoid, if you remember. And the other parameter is C, which corresponds to the horizontal axis. And this is the regularization parameter for the sparsification of the attention. So meaning more C, you get more compact models. So you force more compression of the network. You force to learn with fewer neurons. And the larger the Smax, the larger is the more binary is the attention. More 0-1 based is the attention. So we see that in reality, Smax doesn't matter a lot. So all the curves look like the same within if Smax is within reasonable bounds. And what is important is, or more important, is this sparsification parameter C, the compressibility you want to achieve when you learn the networks. Of course, this is not based in progressive neural networks where you can grow the number of parameters. So here the number of parameters is fixed. You have a fixed budget before the sequences of tasks. And thanks to parameter C, the algorithm can try to learn how many neurons shall I dedicate for this task, how many neurons shall I dedicate for the other, etc. If you put a big C, it starts dedicating very few neurons to the first task. It doesn't learn it well, then and the reverse applies. So if you dedicate all possible neurons to the first task, then for the second and following tasks, you don't have neurons to learn, so you are not able to learn the new tasks. So C is a compromise, and it depends a bit on the number of tasks you want to consider. But perhaps the more interesting thing is that thanks to this schema, to this mechanism, it gives you some nice tools to monitor our neural networks. And this I particularly like it a lot. For instance, if we monitor the attention vectors, we can monitor the used capacity of the network. So here you see the sequence of tasks. So every color is a new task. And you see at the beginning, first epoch, you start using a lot of neurons. But then as soon as it learns the task, it stabilizes to some number of neurons. Then for the next task, you start using a lot of neurons. But as soon as you progress learning, less neurons are used, and so on. So for instance, here we know that we are using 80% of the capacity after the 8 tasks. So this is some information. And this information is general, but you can decompose it per layer. So for instance, here, this is the total cumulative use of neurons in the first convolutional layer of an AlexNet. So you see that after 1, 2, 3, 4, after the 5th tasks, we are already using all the capacity of the first layer of this AlexNet. This is important because it can give you some design hints. For instance, you could say, okay, I'm going to put more filters now on the first and retrain again, or something like that. And we see that the last fully connected layer is the one that still is at 80% capacity, and it's big. Another interesting thing we can monitor, it's knowledge reuse. So again, by looking at these hard attention vectors that we learn, we can see how much knowledge is reused from which task. So we can compare tasks in a pairwise fashion and see if task 7 uses more knowledge from task 2 or from task 1. So in this case, the values are a bit counterintuitive, but you need to account, this was due to the fact that the less, since our budget is constrained, the less neurons there are remaining, the more forced is the network to reuse previous information. Otherwise, it doesn't feel forced to reuse information. That's why numbers basically grow with the task. Another thing we can do is compression. So we have this C parameter that controls compression. So if we focus in one single task, but try to tweak the C parameter a lot, we can compress our network. This is super beneficial for deploying the network in low resource environments, or even for generalization sometimes. So here we did some experiments by putting a little bit more value on this C parameter and focusing on how it could be compressed. And here we see the compression ratio and the accuracy as the training progresses, because we compress the network while learning, because at the same time we learn the network, we learn the attention vectors. And these are the plots, and these are the ground truth accuracies without compression. So we see that most of the time we reach that accuracy. Sometimes we are a bit far away, but not that much. And on the right, you have the table with the exact numbers. So sometimes we reduce the size of the network, depending on the data set, to 1% of the original size. So meaning if the original size was 10 million parameters, the network is only 100K parameters. And yeah. So to conclude, I'm going to give you a bit of a summary. So we have this hard attention to the task mechanism that protects the information from previous tasks while learning new tasks. Interestingly, it only adds a tiny fraction of weights to the base network, because these embeddings, it's the only extra structure that we add. And these embeddings are as big as the number of neurons, not the number of weights, but the number of neurons and filters. So this is much, orders of magnitude less than the number of weights. Interestingly, we can train this hard attention together with the base network with minimal overhead in terms of training time, and using a vanilla SGD, no fancy training algorithm here, to learn these binarized attention vectors. And the approach yields very interesting forgetting ratios, so between 45 and 80% less forgetting than the best baseline for every task. And it has only 2 hyperparameters, and they are very intuitive, and we have seen easy to tune within reasonable bounds. Intuitive because, I mean, one corresponds to the compressibility that you want to apply to the network, and the other corresponds to the binarization you want to apply to the network. So they have some physical meaning. And finally, we have seen that the approach yields to very interesting monitoring capabilities, and it allows the possibility of compression, or if Smax is quite small, that you don't binarize very much the attention vectors, it could even be applied to online learning scenarios where the concept and what you want to learn changes over time. Therefore, you need to forget a bit, so you can control the amount of forgetting with this Smax parameter. So that's it. If you are interested in more, paper is available, code is available, data is public. So thanks for your attention.
If there are any questions, Juan and I will have a microphone, so please raise your hand and we'll come over with a microphone.
A nice talk, Joan. So you put the attention on the head. It's on the attention of your network. So this mask function you do. And I wonder, so another choice could be to put it on the weights instead of on the attention.
Yeah.
Could you say something about the implications of changing from the weights
Yeah.
to the attention?
First obvious implication is the size of your attention that you are learning. So you should have as many, this attention should have as many parameters as the number of weights. This would double the size of the network. And second, I think it's easier to learn and to binarize. It's easier to put a 0 on the output of a neuron than to put a 0 on some weight. The weight unstabilizes the rest of the weights, and it's a bit, but this is intuition, I don't have a proof.
In principle, if you look from a point of view of backpropagation, you are putting weights on a whole column in the
Yeah.
weight factors,
Yeah.
no? Or,
No, in fact, you can decouple it, and because if you know the previous layer and the next layers, you can focus on the weights. That's what we do also in backpropagation.
Okay, thank you.
All right, well then let's give a hand for Joan and